Hello, we are here at the Modelica and FMI conference in Lucerne. My name is Christian Bertsch from Bosch Research, and I'm the FMI project leader. And today we will give a tutorial. In the first part, we will introduce FMI, the basic idea, and give some background on the history, also the technical background, and give a first example how to create FMUs. And then I pass over.
Yes. Hi, I'm Claudio Gomez. I'm an assistant professor at Aarhus University, and as part of this tutorial, I will show you how to interact with a functional mockup unit, which are these simulation components used in FMI.
And I'm Maurizio Palmieri, assistant professor from the University of Pisa. I work on subphysical systems, and today I will show you how to couple different elements adherent to the FMI standard and how to win the trade-off between accuracy and execution time.
When we have seen that, I will give a short outlook on new features of FMI 3, which we will also give examples and give some outlook. So then later we will have the tutorial recorded live here in Lucerne from the conference. Have fun.
In this tutorial, we want to give you an introduction to the functional mockup interface, FMI. The outline is as follows. In the first part, I will present the motivation and history of FMI. Then I will explain the basic technical ideas behind FMI and comment on the tool support of this standard. We will conclude the first part with an overview of new features of FMI 3.0. In the second part, Claudio Gomez will demonstrate working with single FMUs. In the third part, Maurizio Palmieri will show how to interact with multiple FMUs. We will conclude with a demonstration of new features of FMI 3. Introduction to FMI. You can find all the material on GitHub. We will start with the motivation and timeline. The basic idea of FMI was to define a tool-independent, free-to-use standard for the exchange and co-simulation of models between different simulation tools. Here the models are provided in a containerized form that allows for the deployment to different targets. In this way, we can decouple know-how between producers and users of models and between specialized engineers and software programmers. This allows for the massive reuse of models and to some form of IP protection, as the models are exchanged in black box format. FMI 1.0 and most parts of FMI 2.0 was developed in the publicly funded Modelisar project. In 2011, FMI 1.0 was released. Since 2012, FMI is developed in a project within the Modelica Association. In 2013, FMI 2 was released, which today is most broadly used in industrial practice, and which thus is the focus of this tutorial. In 2022, FMI 3 was released with many new capabilities. We are now in a transition phase and see fast adoption of FMI 3. For this reason, we will in this tutorial give an overview of the new capabilities. And since last year, new layered standards on top of FMI 3 have been released that make use of the new features of FMI 3, and we will also comment on them. The FMI standard uses semantic versioning with major, minor, and maintenance releases. Major releases are for non-backwards or forward-compatible changes. Minor releases can introduce new features, but are backwards compatible in the sense that, for example, an FMI 3.0 FMU will also be a valid FMI 3.1 FMU. Bug fix releases introduce no new features, only bug fixes and clarifications, and thus they are backwards and forward compatible. Today, FMI is the leading free and render-neutral standard for the exchange and co-simulation of simulation models. Current releases are FMI 2.0.5 and FMI 3.0.2. More than 250 tools and libraries support FMI. You can view the list of FMI supporting tools on the FMI tools page in the internet. And there you can also search and filter for different tools. And please note that these are the official tools, but there are also lots of in-house tools that support the FMI standards and that are not listed. As mentioned, today the FMI standard is developed in a project within the Modelica Association, a non-profit, non-governmental organization with the aim of developing and promoting open and coordinated standards for system modeling and simulation. Modelica Association defines the Modelica language and libraries and the FMI family of standards. Besides FMI, there is the System Structure and Parameterization Standard, SSP, which can describe, for example, the connection of multiple FMUs and parameter sets for FMUs. The Distributed Co-Simulation Interface, DCP, describes distributed co-simulation in soft real-time. And EFMI, meaning FMI for Embedded Systems, standardizes several transformation steps from a model to embedded software. The FMI project has three groups of organizational members. The steering committee, which defines the roadmap and takes decisions. Contributing members that participate in the development and maintenance work of the standard. And the advisory committee that can give feedback, formulate requirements and ideas. Let's have a look at the technical fundamentals of FMI. The basic idea is that we separate between the tool where the model is created and the tool where the model is simulated. The first one we call the exporting tool, the second one the importing tool. And the functional mockup interface describes in which form a model can be exchanged between them. The good thing is that this is specified in a tool-independent way so that the exporting and the importing tool do not have to know from each other. And you do not have to develop n times n different interfaces. The basic steps that are performed are: first, develop the model in a suitable tool. Second, export it according to the functional mockup interface standard in the form of a functional mockup unit, the FMU. Third, import the FMU in the tool where you want to simulate it, possibly in a co-simulation with other models. Fourth, perform the simulation there. The original scope of FMI were mainly models described by ordinary differential equations, ODEs, with events. You need a numerical solver for their solution, and you have to distinguish between continuous and discrete variables. There is always a notion of time, or more generally, an independent variable, which could also be an angle or distance. But today FMI is used in a broader scope, for example, also for purely algebraic equations, or to describe complex discrete behavior with clocks and model partitions in FMI3. So there is a very broad scope of additional use cases, such as virtual electronic control units, ECUs, or AI models, and many more. Let us briefly introduce the concept of co-simulation. It means the coupling of several simulation programs in order to compute the global behavior of a system that consists of several subsystems. These subsystems are coupled in the sense that the behavior of each subsystem depends on the behavior of the remaining subsystems, so that the co-simulation must be computed in a step-by-step fashion. Each simulation program is responsible for computing the behavior of a subsystem using the outputs produced by the other simulation programs. Please note that there can be an additional error introduced by co-simulation that has to be limited to an acceptable size by using a suitable co-simulation algorithm and communication pattern. Most prominently here, the step size has to be selected in a good way. Now we are ready to explain the functional mockup interface standard. It defines the interface between a model and a simulation environment. And it consists of the definition of an CAPI, that is an application programming interface, an interface description, model description XML, for the individual model according to a defined schema, and the definition of the exchangeable unit, the functional mockup unit, FMU, which technically is a zip file. It is important to note that the FMI standard only defines the interface of a single FMU, not the co-simulation algorithm or solver for multiple FMUs. Let's now have a look at the FMU, that is the model container that can be distributed. Technically, it is realized as a zip file with the ending FMU, and it contains the model description XML file with metadata containing information on the model variables, the interface, and certain capabilities of the model, and to a limited extent also the model structure. The model representation in the form of binaries for multiple platforms in black box format or source code, that is typically C code, which could be recompiled for other platforms. And optionally, it contains also other resources, for example, parameter files, documentation, icons, and port definitions. And there is optionally an extra directory, which can contain additional information defined in layered standards. There are two different kinds of FMUs in FMI 2.0. Model Exchange, ME, versus Co-Simulation, CS FMUs. Please remember that we typically have a model that contains ordinary differential equations. And one of the main differences between Model Exchange and Co-Simulation FMUs is where the solver of these differential equations is located. In Model Exchange, the FMU contains only the model equations, not the numerical solver, which then at simulation is taken from the importing tool. In Co-Simulation, the model and a suitable solver are encapsulated within the FMU. Both kinds of FMUs have their use cases and pros and cons. Model Exchange FMUs provide a very tight integration of the model in the simulation tool. This leads to a complex interface between the importing tool and the model. And the importing tool must provide a suitable numerical solver for the model. One use case for Model Exchange is, for example, also when tools that don't have Modelica support license a Modelica compiler, then often under the hood, Model Exchange FMU is created and integrated in this simulation tool. A co-simulation FMU, there the model and the solver are encapsulated in the FMU. And here the interface between the importing tool and the FMU is simpler, because they communicate only at discrete points of times. And in between, the FMU and the included solver can, for example, take smaller variable time steps which are not visible to the outside. Here, one has also the freedom to select a co-simulation master algorithm and a suitable communication time step between the importing tool and the FMU to reach stable and accurate simulation. Co-simulation FMUs are most prominently used in industrial use cases. We want to have a closer look at the calling sequence for the simulation of co-simulation FMUs. So typically one sets the input of the FMUs with an FMI set call. Then one triggers the calculation for the next time interval and advance time with an FMI2 do-step call. And then one can inquire the outputs that have been calculated with an FMI2 get call. These outputs are then processed by the importing tool and can, for example, be passed to a connected FMU. Once again, we want to emphasize that no particular co-simulation algorithm is specified by the FMI standard. This standard deals only with one model and its interface to the outside world. Now we want to have a closer look at the model exchange interface. The main idea here is that the model exchange interface exposes the right-hand side of a hybrid ordinary differential equation system to the solver provided by the importing tool. The importer controls the data exchange and the synchronization between the FMUs. And the numerical solver itself is not part of the FMI standard. This solver provided by the importing tool is responsible for advancing the overall simulation time, exchanging input and output data, computation of continuous states, by time integration, and triggering of input clocks and event handling, if you have clocks, for example, in FMI3. When we have multiple FMUs, each of the FMU provides the interface according to the FMI standard. And then the importing tool needs a numerical solver in the case of model exchange FMUs, or a co-simulation master algorithm for co-simulation FMUs, or a scheduler for scheduled execution FMUs, which we will see for FMI3. But these algorithms, the numerical solver or the co-simulation algorithms, are not defined by the FMI standard, but are provided by the importing tool. The properties of a specific model are described in the model description XML file. It contains all static information about the FMU, so for example, which interface kinds, model exchange, co-simulation, scheduled execution are supported by the FMU, the information on the model variables, so which inputs and outputs the FMU has, which parameters it has, and also some information on the model structure. And here on the right you can see, let's say, the beginning of such an XML file, and also further examples are provided for the reference FMUs from the FMI project. Additionally, the FMU can expose here in the model description XML file certain capabilities, for example, that it needs an external execution tool, or if other optional properties are supported by the FMUs. It is very beneficial if the FMU is self-contained, so that you can just take it and simulate it without the need for installing additional software. That's what we call a self-contained FMU, and this is the standard case. But there is also a variant which we call tool wrapper FMU, and here this flag that we mentioned on the last slide indicates that the FMU is not self-contained, but it needs additional software that has to be installed on the target machine. For example, certain multi-body simulation tools, there you can get an FMU where you need a tool installed in order to execute the FMU. FMI today is supported by more than 250 simulation tools, and here we provide the link to the FMI tools list that is maintained by the FMI project. There you have typical exporting tools, so typical modeling and simulation tools, tools for creating software, creating virtual ECUs, for example. Then you have as importing tools also the typical modeling and simulation tools, but also specialized co-simulation and integration platforms, or lots of libraries for different languages like Python, C, C++, Rust, whatever, to trigger the simulation of FMUs. On this tool list by the FMI project, you will see certain tools that have the golden star and a link to examples and compatibility information. And this replaces the cross-check that was very successful for FMI 1 and 2 to improve the maturity of tools. And here, now the tools themselves can provide information how they tested their implementation, provide example FMUs for exporting tools, and report on with which other FMUs they have tested their implementation and with which checkers. And this is very beneficial for users to see how good the implementations have been tested. What is also important that there are several checkers for FMUs available on the FMI website. Here you find them in the validation tab. There is the FMU check, which is based on FMPy and does a static check, so it cannot simulate the FMU. It checks mainly the XML file. It validates it against the schema. There is FMPy, an open source Python tool to simulate FMUs, which can validate also the FMU. That is the XML file mainly, but it can also simulate the FMU so that you can check whether the FMU is simulatable. And there is FMUSim within the reference FMU repository, which is a standalone tool which can also validate the FMU, the XML file, and also trigger a simulation. And there is the VDM checker that does also additional checks. So it's good practice when you get an FMU from some tool where you do not have much experience that you check it with one of these checkers. One must be aware that while the FMI standard describes the interface, the exporting tools can have additional mechanisms regarding licensing. And this can be technical restrictions, so that you, for example, need a connection to a license server like XLM, or this can be legal restrictions, so that there are restrictions on the distribution of the created FMUs. So here, please refer to the documentation provided by the exporting tool vendors. And one can also store such information in the documentation folder of the FMU. What we saw until now was mainly for FMI 2, but now FMI 3 has been out for 3 years and gets rapidly adopted, so it's good to have a look at. So FMI 3 was released in 2022, and here was an overview of the conference in 2021, where we saw FMI already broadly supported by many tools and broadly used, but new use cases required new features. For example, FMI is heavily used for virtual electronic control units, and here new features for the more discrete behavior of these use cases were needed. There were advanced co-simulation FMUs, where the advanced algorithms needed new features. The general trend for larger simulation systems with multiple FMUs, and for example also with discrete behavior and events that have to be synchronized across FMUs, and new use cases like machine learning, where for example adjoint derivatives are needed for the efficient training. And FMI 3 addressed all these new needs by making the API better and richer for these new use cases. In FMI 3, we see the two kinds of FMUs that we already saw for FMI 2, model exchange and co-simulation. And they are still the most prominently used ones, but there is a third variant for scheduled execution, which allows for the coupling of several FMU with one external scheduler. But one must say this is not really in industrial usage yet. it's an outlook. For now, you can stay with model exchange and co-simulation for most use cases. But here, these two kinds of FMUs have got new capabilities that we will see on the next slide. The main improvements are event mode for co-simulation, so where we get away with the typical fixed time step co-simulation information exchange. Here we can have events that indicate that something changes discontinuously, for example. We have the intermediate variable update, where even between the communication points in co-simulation, information can be exchanged between the FMU and the importing tool. We have the clocks to describe discrete behavior and the synchronization of events. We have new variable types that are much more fine granular. So, for example, different integer types, also the binary variables, array variables, which are very important for efficiency, because in FMI2 we have only a naming convention to support arrays, but these are individual variables, which is not very efficient. And in FMI3 we have arrays of multiple dimensions. We have terminals and icons for the grouping of variables. We have FMI for scheduled execution, which I mentioned on the slide before. And we have the preparation for layered standards, which are extension mechanisms that build on top of FMI. And this supports both better performance and accuracy and new applications. And we will see more of these features in a demonstration in the part 4 of this tutorial. Now I want to give a hands-on presentation to demonstrate the usage of FMI. As an example, we have here a Modelica model for an electrical machine with a simple driveline. So this is our reference example, which we will then export as FMU and also split up in multiple parts to export it as several FMUs, which are then imported in an importing tool and simulated there in form of multiple coupled FMUs. Here we simulate for 1 second, and this electrical machine is controlled. The voltage is controlled by a PI controller, and here we get a step for the desired angular velocity from 0 to 10 radians per second at time 0.1, and the load torque jumps at time 0.5. And we will see here that at time, here's the resulting angular velocity of this electrical machine. We will see here the jump at time 0.5, so there's some dynamics until this 10 radians per second is reached. And here we have a little jump at this time 0.5 where the load torque jumps. So when we then simulate this as FMUs, we can have here a look at this reference solution. And here is depicted how we can split this model, which we could also export as an overall FMU, in 3 different parts. So we have here more the physical part. This is this electrical machine with a driveline. And then we have the controller, this PI controller, and we can group the stimuli that come to the model also in one FMU. So we can export this as 3 different FMUs, and then we can import them into the importing tool and simulate them. So here we see the options when we export the FMU from Daimler in this case. So you have learned in this tutorial about the difference between model exchange and co-simulation FMUs. So here you can select which type you want to export and also which solver you want to select for the co-simulation FMU, which is then also packed into the model. You can select which version of FMI, you can select which binaries, And also in the case of here working on a Windows machine, if you have the Windows subsystem for Linux, you can also include Linux binaries here in this FMU. And you have additional options when creating the FMU. And once you have exported the FMUs, you can then import them back into Daimola, connect the different FMUs, and there we will see then also the results. And we will also do the same, importing these FMUs created from Daimola. We can import them also, for example, in MATLAB Simulink. And there we can see the tool-independent behavior of the FMUs. So here you find this in the Simulink library browser. You have under Simulink Extras the FMU import. That's the FMU import natively provided by the MathWorks. And then you can import these 3 different models and simulate them. We see here the tool Daimola, Modelica-based tool. And we have here loaded the model that we want to use as an example. So I will first simulate it to get a reference solution. So here now this Modelica model gets translated to an executable simulation program, and we inspect here the angular velocity. And as seen in the slides, we have this output here over this 1 second. And now we can export this as an FMU. Here you see here this options, so whether you export it as model exchange or co-simulation FMU, and different variants. So we will do this here. So now the Modelica model gets translated to an executable program in a C code or binary form, and then this is encapsulated with the FMI interface to a functional mockup unit that then can be imported in different tools. So we did this first now for this overall model, but here, as mentioned, I have split this also here in different tools. Here, for example, for the stimuli, for the controls, for the drive, and I have exported each of them as an FMU. And now we can import them. So I will create here a new model in Daimola, and I will select here these FMUs that I have already exported previously. So we'll go here to the corresponding repository, and I have here this stimuli FMU, which I can drag and drop here to the model. And as the model here in this case was exported both containing model exchange and co-simulation interface, I can select here which one I want. I select here the model exchange interface, and now I have here in my library browser, I have here the stimuli FMU, which I can drag now here to the model, and I do the same with the controller. And also with the drive line. Now we can connect them. So here, this is this desired angular velocity, which is here mapped to the omega desired. And we can connect this to the drive line. So this gives the voltage for the electrical machine. And here we have the load torque from the stimuli, which is also passed to the electrical machine. And we close here the feedback loop, where we measure the angular velocity and pass it to the controller. Now we have this in form of FMUs in Daimoler, and we can trigger the simulation. Here we see the reference solution from the one Modelica model, and now we simulate these 3 FMUs. And we can also here depict the angular velocity from here, in this case, from this driveline FMU. And as expected, we get here the same result. So here in this case, even though this is a Modelica tool, each of these models that we see here is now a black box model with the functional mockup interface, which we have connected here and simulated first in the tool Daimoler, which is the same where the models have been created, but it's good to see that already here it works, and then we will see how we also can simulate this in another tool. And I just see here that we have already mixed model exchange and co-simulation models, which in this case gave still the same result. We could also have selected here only model exchange FMUs.
Hi everyone, I am Claudio Gomez and I'm here to present the second part of this tutorial. Now, due to a technical fault, the first 5 minutes of this video have been recorded as a voiceover the original recording, and then after 5 minutes the original recording starts in, so there might be a difference in the audio level. This is the agenda for today. We'll first start with validation, then we'll work with FMUs in FMPy, the tool we will be focusing on. And finally, we'll simulate FMUs from the code from Python using Jupyter Notebook. These FMUs are just zip files, and if you have the options on your file system to display extensions, you can change the extension of the file to tell the operating system that this file is actually a zip file. So this is the little option you need to enable if you wish to do this. Otherwise, you can also do it from your IDE typically. So if we change this to a zip file, we can then open it by double clicking. Now inside the FMU you can find the model description XML file. This is what simulation tools will use to find out what the variables, input and output variables are. You have some documentation, you have icons. So if you open the XML file, you can now see that all the variables declared in the model are here, and we can see their types, we can see their names, as well as their value reference, the code that the software will use to interact with the FMU when setting and getting those variables. So here you can see where the output variables are by searching for output. You can see that there are parameter variables. You can see input variables, for example, the voltage. You can see here the output variables, the angular velocity. Now let us validate this FMU on the FMU Checker website. This is the link. You can find it in the documentation. You can scroll to FMU Check under Validation, and then clicking on Validate your FMUs, you will then be instructed to upload an FMU, which is we uploaded the Drive FMU, and after the validation has passed, you can also see all the information, metadata about the FMU. All the variables, basically the same things we were seeing in the model description XML file. Now let us focus on using FMPy. Back to the agenda, we will be working with FMUs using FMPy. So the first part is to install the tool. For that, you can head over to the website. I already have the tool installed, but I will just show you the website. To install, you press pip install FMPy complete. This will work in most systems. If that doesn't work, you can check the website and see the instructions for your platform. You can also see the command to start the GUI of the tool. As well as other more advanced documentation. I would recommend you follow these steps on your own after watching the tutorial to make the most of this.
Here's the GUI of the tool. I can drag and drop an FMU into this to see its specification. And here you can see the metadata of the FMU, and you can also run a simulation with it. But you can see, for example, the inputs here. It's an input because the icon shows a little arrow into a circle, and a little arrow out of a circle is an output. And then, so I have two inputs here, and then the rest are model variables. They're local variables or parameters that you can change in here. Go back to the script, make sure I'm following more or less the same. If the model has the documentation, you can also find it in these menus. So here you can find the contents of the zip file of the FMU. Here you can find documentation of the FMU. Naturally, here you can see the simulation parameters in case you need to run one. And here later you'll be able to see the logs. So when you run a simulation, it produces logs, and you can see them in this menu. This is showing you the different parts here. And there's a plot which is disabled now because we haven't run simulation yet. Right. Let us run a simulation. So here I'm running a co-simulation. I'm setting a time, 1 second, the default. These values come from the default experiment, which is described in the model description XML file. So it helps you to get started without thinking too much. And I can check the other parameters. This you can set the tolerance for the error. I'm using a variable step size, as Christian mentioned, a variable step size solver. I can define how many samples I want to get as an output. I can define potential inputs. In this case, nothing. I wish to log FMI calls and debug logging, show everything, and I am set to go. That's it. It run. It's not plotting anything. I think I need to press plot here. I can see the angular velocity as an output. This is a 0. The input, the velocity, the input. I think it's a set velocity, right? Set velocity is at 0. I think this is set voltage actually, not velocity, because unit is volts. So set voltage. Okay, and let's make this move for now, because we're not making it move anyway, so it's not really. Yeah, we also don't have a set torque, so there's nothing interacting with the drivetrain here, making it move. So how do we do that? We need to define an input, right? Well, ideally, we'd connect this to other FMUs who then have a speed controller or something like that, who then does the rest. But in this case, we'll just define an input and hard code the inputs into this FMU. If I don't know anything, there's a little hidden feature here, which is in this 3 dots. This little arrow, I can actually create a dummy input file, and it will read the inputs of the FMU and give you a CSV file created from scratch. That's a useful feature. No one should have to edit CSV files manually. And in here, it gives you time, voltage, and these are the 2 inputs, right? This is good to get started. Now you need to define a step function, and the way to do this is you only register in a CSV file the point at which the inputs change and how do they change. So I can say 0.5 at 0.5 seconds, I wish the step voltage to increase to 10, right? The load torque can remain at 0. And, oh, sorry, actually, this, as far as I remember here, you mark the 2 points before and after the step. So you mark it like this, for example. And this would represent the, yeah, compilers trying to be smart. But, and here you would, so what we're saying is, I'm giving it a step input on the V input. I have an example here to avoid, yeah, exactly. So I have 50 at the beginning just to get it going, 50 volts to the input, and then at 0.5 we're defining. So notice that we set the continuous part here up to 0.5, and then at the same time we describe the left hand side of this step to the new voltage. I see some of you frowning. Is this clear? How we describe the inputs? Yeah. Okay. Maybe I can zoom in. Right. Now we can go in here and specify this file. And now we can run simulation again. And now we see something out, right? So we can see the voltage is always at 50. The load torque decreases to minus 100 after at 0.5 second. And this has the effect of slowing down the car. It's a bit like starting to go up if you're driving. So it slows down the car, but then kind of oscillates a bit, and it settles at a lower angular speed, which is why we need the controller, right, to kind of regulate the velocity, the voltage, to ensure the same velocity is kept. Questions here? Right. Oh yeah, you can validate this FMU as well from here. So on the tools menu, you can validate the FMU. So no problems have been found. This is the same as the web app that you saw. And you can also compile a platform binary for the drive FMU. So this FMU actually has sources. You can see typically under the sources folder on the zip. And so you can try to compile it to a different platform. For example, well, in this case, I'd probably be more successful if I try to compile it to a Windows 64. I will not attempt that because I will likely break the demo. But try this at home, right? You will at least get compiler errors that you can start to work from. If you don't have the right, yeah, you need all the dependencies, etc. Ideally, everything should be under the source files, but ideally is just an ideal. Yes. The logging. Remember, I went into this option here to say to log. And so now I can go over here and I can selectively enable info messages, so I can see sundials is being used. This is how much the simulation took, and there are some other statistics here. If you really want to see all the FMI functions being called, then you enable the log FMI calls. And then you can see, so these functions are all defined in the FMI standard. And you can see their calls and the parameters that were used. So instantiate, set up experiment, then it set enter initialization mode, it set the initial inputs, exit initialization mode, did query the initial outputs of the FMU, and then it actually gets there. So do step, queries, sets the inputs and queries the outputs, do step again, and so on until it reaches the end of the simulation. Any questions here? Good. How do you do if you wish to interact with the FMU programmatically, right? So FMPy is also a Python library. It has a GUI, but you can also interact with a Python library. Well, the easiest way is to generate this. Oh, I'll close the window. Is to generate a Jupyter notebook from the FMU. So I'll open the same FMU I had. I'll go here and say create Jupyter notebook. And I have a demo here. I'll just override this one. This will then ask you if you want to start a Jupyter server to actually see the Jupyter notebook. Have you used Jupyter before? This notebook? Yep. Okay, great. You could run this from a Python script. So don't be worried if you don't recognize the Jupyter interface. It's just a glorified way to interact with a Python interpreter. So we have it running, and it actually generates a bunch of Python scripts, importing the library and giving you the code. If you run it from the right starting directory, which I'm not sure it is running at the moment, it will locate this FMU and then run a one-off simulation with it, just like we did from the user interface. Let's run this. Hopefully, yeah, it works. And it's plotting here, it's plotting the result. So because we only said I want to see the angular velocity as an output. Let's see if we place the voltage here as part of this list. Hopefully, it should plot here. There's other parameters for this simulate FMU function. One way, I will open it in VS Code so I can show you the library function as well. If you're used to reading Python code instead of the documentation, this will be familiar to you. But if you go to the Python function of FMPy, right, it's an open source tool, and we're running Python, so you can come in here and change the code to your liking when things are not working. But you can see all the parameters you can pass in here, like the input. I can pass an input CSV. I can pass a sequence of inputs. I think I can pass the input CSV somewhere here. I had a note. Give me a moment. Yes. So you can read a CSV file, just like you did from the interface, the same CSV file, and then simulate the FMU passing that input, right? So in the provided source files of the demo, you can find this notebook here. If you run this, running it now from VS Code, it's the same. You then get a behavior as we saw in the graphical user interface, plotted with a nice library. If you wish to go deeper, so let's say you want to actually have a for loop to run the simulation yourself step by step and then set different inputs and so on depending on the time, etc. Right? Then you can find an example of it in the documentation. So in the README file, the example you're looking for, so you find a few more examples on how to use this. But these examples are particularly helpful under advanced usage. And you can find the custom input script as an example, you can then try out. This works out of the box, so you don't need to download. It actually will download an FMU for you to run it. And over here, you define the usual simulation parameters, but here you can read the model description, parse it yourself. You can then find the different inputs and outputs in this big dictionary representing the model description that you've parsed. You extract the zip file out of the FMU, then you create this FMU2 slave. So this is the Python object representing an instance of that FMU, right? And then you can run through the usual co-simulation loop, right? So instantiate, and during the simulation, you can then set the inputs as you wish you want. This also allows you to control better how to plot things and what to plot during simulation. Don't forget to clean up, of course. Any questions? So let's just recap a bit. I've shown you a way to validate the FMUs on the website. This doesn't require any installation on your side. You just want to do a sanity check on the FMU. Then we started playing using FMPy. We showed you how to play with an FMU, right? How to open the FMU, inspect the parameters, etc. And also how to run basic simulations. And I recommend you always do this before you try and do something bigger, especially if you're interacting with other team who's providing you the FMU. You want to do these things early on to kind of find the problems early, right? And there will be problems in our experience. Showed you how to run simulations with a custom input file. It's a good idea. Then if you have source code, it happens that you may have to run the code simulation on a different platform, like a Linux machine. You can also use, if the sources are provided, you can use FMPy to try and compile that to a different platform. And if all the files are there and the specification is correct, then it should be possible to compile it to a different platform. Then we showed you how to go one level deeper with the FMPy library and actually interact with the FMU from Python in a script. And then there are some examples online showing you how to then effectively code your own simulation with one FMU, how to connect these things together.
Good afternoon, everybody. So now we can resume with the tutorial. So we are now approaching part 3 of this tutorial. And now we are going to connect multiple FMUs together. Christian has already shown us how to do this on MATLAB and DimeLab. Now we will see another tool for this kind of operation. We are going to see the tool named IntoCPS application. A little bit of history. IntoCPS is the name of an European project that was on in 2013. And it created its own master for FMI simulation and its application for simplifying the management of the FMUs. So if you look online, you can find the okay. If you look online, if you look on internet IntoCPS association download, you will end up into this page with the latest release. Now, the latest release 5.0.1, is very new, is a clean restart of the application. It is still missing some relevant baseline operations that are available in the version 4.0.7. So for this tutorial, we are working on version 4.0.7, which still supports FMI 2.0. So you can choose the kind of executable for your platform. There is AppImage for Linux, there is Excel for Windows, and there is also the one for Mac. Once you download it, you will have just an application that I have already downloaded and moved into any folder of my computer. Now I will show it with the Ubuntu graphic implementation. On the slides, in part 3 of this tutorial, you will see with the Windows design, but basically it's the same. On Mac, there is a slightly different version, but the overall behavior of the application doesn't change. So if you double click on the application, you are actually launching the application. This is not the image that appears when you start the application. I have already run the configuration of this tutorial. So basically, this application allows us to combine many FMUs together. Now, combining the FMUs mainly consists in 2 tasks. First task is to actually retrieve the FMUs. This is independent from the application. It requires your skills in searching on the internet, on producing your own FMUs, and you can generate many FMUs. You can retrieve the FMUs that you need for your system. And of course, the first thing you need to do is some sort of validation. And here is the helpful function of Into-CPS application. But then you have to connect the FMUs. Now, generally speaking, this is apparently a simple task, as long as all the naming of the variables combine between the different FMUs. In our case, we have prepared the FMUs, so the variable named v as output of one FMU is named v as input of another FMU. There might be some troubles in which different teams, different countries give different names to the variables. General applications help with this problem by filtering all the variables with different types. So, for example, integer, floats, Boolean, they get filtered out when you are creating connections. So now we have to create the connections between the FMUs. So first thing first, we need to create a new project. So on the Into-CPS application, file, new project. We can choose the name of the project, for example, tutorial 2025. And then we need to choose the folder in which we are going to save the project. So we can open folder. I will go to the folder that I have created, tutorial project. My suggestion before doing this, create a new folder, new empty folder. You can select your folder, then click OK and create. Now, at the beginning, in your project, there is nothing, of course. There are only a bunch of folders. If we move actually into the folder, you can see that the Into-CPS application has created a number of folders in which you can move the elements of your project. The main folders are FMUs and multi-models. Of course, Into-CPS provides some other features that can be interesting. For example, suggest the uses of SysML for high-level modeling, or model checking to perform a model checking. And now the first step is to include the FMUs that we have somehow gathered into this project. So we have to move the FMUs into the FMUs folder. On the GitHub of this tutorial, you can find in part 3, the folder part 3, example into CPS application, a project already created with the 3 FMUs that Christian has created about the power drive system, so control, drive, and stimuli. You can download them and move them to the FMUs folder. I've done it before, so I can find it here. They are just files, so it's just copy and paste. And now, on the application, you can see these 3 FMUs on the left part of the graphic user interface. Okay, now we have what we need to start. We can start modeling the connection between these FMUs, creating a multi-model. So you move the cursor on the multi-models on the left, right-click, new multi-model. You can choose the name of the multi-model. I always choose the default name, multi-model new, new. Okay. Now we have 2 tabs. In the first tab, we have the overview, but at the moment it is completely empty. We can close it. And then we have the configuration. So now we have in this project 3 FMUs, but now we have to import the FMUs into this specific configuration, into this specific multi-model. So we hit the edit button and we need to add 3 FMUs. So 1, 2, and 3. We have to define an identifier for the FMU, and we know they are control, drive, and stimuli, so we can name the identifier control, drive, and stimuli. Control, drive, and stimuli. So now we have 3 FMUs. We need to connect the key to the actual FMU. Since we have moved the FMUs in the FMUs folder, just by clicking on File and selecting the FMUs, we are creating the binding between the identifier and the FMU. So, control, drive, and stimuli. As you can see, the app is at the same time checking that it is the FMU is supported, meaning that the FMUs in the binaries folder within the zip has the executable for the platform that it is being executed on. For example, control, if we hover on supported, this FMU is supported for Linux 64 and Windows 64. We are on Linux 64, so this is okay. Now, according to the standard, you can define more instances from the same FMUs. This is not our case, so we will have just 1 instance for each FMU. But the creation of the instance is not automatic. So we have 3 FMUs, and for each FMU, we have to create an instance. So we select 1 FMU and add an instance, select the other and add an instance, we select the third, and we add the instance. And so now we have created 3 instances. And now comes the most important part. We have to connect the instances of the FMUs. So the application automatically reads the model description XML file within the FMU and knows its output and input. So we have to connect the output of one FMU with the input of the other FMU. So we can start by stimuli. We click on the stimuli instance. So we can see that it has 2 output variables. And now comes the ability of the user in recognizing and combining the FMUs. So I want to connect the desired angular velocity. I know that this is an input for the control FMU, so I connected to the instance of the controller FMU, and we did a good job, and the variable names match, so it's kind of easy. Then we have also so now we have created the connection between stimuli and control. And we have to do the same from stimuli and drive. So load torque is the name of the variable, the output variable of stimuli FMU. This has to go as an input of the drive FMU. And we click on drive instance, and we find the input variable with the same name. Now we connect, and now we have created the connection that goes as outputs from the stimuli FMU, input from control, and input from drive. So now we move to control. Control only has one output, voltage. Can select its output. And we know that this is an input to the drive. So we select the drive instance, and we create the connection between the two variables. Finally, also drive as an output, and this one should be retrofeedback to the control. Done. So we have created the 4 connections that we have seen when Christian has introduced the case study of the power grid diagram. If required, we can also set different parameters for each instance. So for each instance, we have some series of parameters, and we can, for example, add one parameter and set its value. When the value is not set, the XML file within the FMU has the default value. So we don't need to explicitly set the value of all the parameters. There is a default value. So we don't need to do it for this example. And we can hit the save button. So we have saved. In the overview tab, we can see an overview of the connections. So V is connected with V, W with W, W desired with W desired, torque with torque, load with load. Now we have created the multi-model. Okay, we are ready to start our co-simulation. So right-click on the name of the multi-model, create co-simulation configuration. The name, again, I usually use the default name, co-simulation. Now we have 2 tabs. The first tab, we can define the start time of the co-simulation, which is usually 0, and the end time. We have seen a co-simulation made by Christian with end time 1. So we change end time to 1 to match the one that we have previously seen. Then we can choose the kind of algorithm, master algorithm, to execute the co-simulation. In our case, we will use a very simple one with a fixed step size and with a step size of 0.01. So we change the default value to 0.01. There are other elements that we can change. For example, visibility to change the visibility of the logs. If we want trace, error, global warning. With stabilization, we can implement some refined algorithm for the IntuCPS master algorithm. With live plotting, we can choose which variables to plot during the co-simulation. And we might be interested in adding a graph that shows the angular velocity and the desired angular velocity. So we select the 2 variables that we are interested in looking during the co-simulation. Result saving allows us to choose which variables are saved in the resulting CSV file. All the connected outputs are saved by default, so we don't need to change these elements. Others allows us some important features of IntoCPS, such as the possibility to slow down simulation to real time, or some kind of synchronization with other tools, or to simplify the visualization of the information, and parallelization to increase the speed of the co-simulation. Finally, with post-processing, we can write our own Python script for analyzing the data and provide it here as input for gaining more knowledge on the result. We can save this configuration, and then we can move to the simulation tab. Now, I'm having a green message stating that the co-simulation master algorithm is ready. By default, it is not already being launched, so I will just stop it and launch it again. So I have closed it on the console. So this is the default message. And in order to launch this master algorithm, we need to download it before. It is, you can find it when you open the window and the show download manager. In the latest release, you can find the two master algorithms of IntoCPS. In particular, the COE, that is the very first version of the master algorithm, and the newest one, Maestro 2, that is more efficient in time execution and also provides more customization. I have downloaded the Maestro 2 already, so if you click on this button, it starts the download, and then launch it with the button launch. Now we are ready to start our simulation, so we can hit the simulate button. And in the graph, we have the results of our simulation. We have the desired angular speed and the actual angular speed, which is oscillating around the desired value at the beginning. And then, since we haven't changed the load torque, it is changing also at time 0.5. So we have successfully launched our first co-simulation. When we click on the Open Results button, we are prompted to the folder in which we can find the output CSV, which contains all the evolution of all the variables, the selected, the connected variables, and we can find also the configuration of the co-simulation. So this JSON file has been automatically created. I'm sorry, it is automatically created on one line, but it's it can be easily changed. And basically, all the JSON are automatically created by the IntoCPS application. Now, this is very good for validating our system. So for validating our FMUs, their connections, being sure that we have created the right connections. But when we want to execute many simulations in a row, it is kind of difficult to tedious to run all of them in the application. So our idea is to use the same tools from command line. Remember that the use of the application is still suggested first operation because it creates all the JSON that we are then going to use from the command line interface. So we have created the JSON, with all the information, with all the links, the connections that are required for our co-simulation. And now we move on to the second part of this third part of the tutorial, which involves the command line interface. For this one, I prepared a Jupyter notebook, and you can launch it directly from using Colab, directly from the GitHub. So our GitHub is FMI Beginners Tutorial 2025. If you click Open in Colab, you will open. Just let me start it again. You will open the Jupyter Notebook on the Google Colab. So this one will give everybody the same starting point, the same environment. I suggest we execute the run all cells at the beginning, and then we comment each cell separately. So as you can see, for example, the first one requires some time. It is making sure that the OpenJDK 21 is installed, and then performing some controls on the Java version, and then we are downloading on the virtual machine the GitHub itself with all the FMUs already created and ready for use. Then we start importing some dependencies for simplifying with the plots with from Python. We move in the specific folder of this part, and then we download the Maestro, so the co-simulation master algorithm of the IntuCPS application. This is a specific link to a version that has been slightly modified for simplification during this tutorial, but hopefully this will be the new release of the Maestro algorithm, the master algorithm for the FMI. We define the function for simulation. The first parameter is the configuration, the JSON, that has been created by the IntuCPS application. And then we define also start time and end time. So this is the definition, which basically means that the command, the co-simulation, can be executed with a simple Java instruction from terminal. And so we have prepared our environment. Now we simply show one example of JSON generated by IntuCPS application. This is the case of a single FMU, just to start with. So this is the single FMU that contains all the elements of the model. So one FMU, within we have stimuli, control, and drive. We are interested in logging the variable W. We have a fixed step with step size 0.001. And we have just this information about the level of informations logged by our system. And we simulate from time 0 to time 1. We have the output of the Maestro executable file. We can see that we are using specific plugins such as debugging logging, Jacobian step builder, initializer, and again Jacobian step builder, and we get all the simulation done. At the end, we have created a file named outputs.csv. With this file, you can show this file. So we can plot it with some simple Python functions. and we get the same results that Peter showed, that Christian showed us in the first part of the tutorial. And this will work as our baseline, because now we are going to address the difference between the case in which we embed all the system into one FMEU versus the case in which we split the system into 3 FMEUs. So, again, we provide another JSON that is the one that we have just created. 3 FMEUs, 4 connections, no parameters given. We are simply using the default values. Fixed step algorithm size 0.001. We simulate, we basically have the same feedback from the Maestro executable, and then we print it. And now we can see, we can already see, because we are all trained in simulation, that there are some small differences with the behavior of W that we have seen before. We can actually do something very clever. We can run a co-simulation with 4 FMEUs. The baseline that is not connected with the other, and the 3 FMEUs connected together. This is now part 2. So now we have another JSON. In this case, we have 4 FMEUs. Only stimuli control and drive are connected. We are interested in showing also the W of the baseline. Again, as simple, we simulate from time 0 to time 1. And now here we can see, in particular here, that there is a small tiny difference between the baseline and the case in which the 3 FMEUs are split. The reason is related to the size of the step size, because the FMEUs are communicating with a sort of delay of the step size. So it is important now we can measure the error. So for example, the sum of the evolution of the W squared over time. We have a value, in this case is 8.2, and now it's based on the different, on the experience of the user and the specific case to state if this error is tolerable or not. But what can we do to reduce this error? I say that this error is related to the step size, so we can decrease the step size. And now, here there is a Python code to basically run many times the same simulation, just changing every time the step size. And basically, all the outputs. But as we can see, we have 2 metrics. One is the accuracy that we have used before, the square of the W variable summed over time. The other one is the time required to actually perform the co-simulation, to execute the co-simulation. And we can see that with smaller step size, we have a smaller error, and we are happy, but we have also the higher execution time. So the fact is, there should be a trade-off between the accuracy of the system and the time required for the execution of the co-simulation. Okay, am I on schedule? Okay. So the idea is, how can we win this compromise between error and accuracy? This is like part of the research activity on FMI, defining, working on algorithm for the master algorithm to find the optimum step size, work on adaptive step sizes. But lucky for us, FMI 3.0 adds a very interesting feature that helps us win this compromise. And it is the event-based co-simulation. Basically, now we have just another part to install the FMPy that we have seen with Claudio. And we work just on a slightly different use case to emphasize the result. We work on a bouncing ball, which is a simple ball that is bouncing. It bounces always less and less until it stops. So we have an FMU with the bouncing ball. We simulate this FMU, plot the result with a step at 0.1, and we can see that we are missing the moment in which the ball, the first moment, in which the ball touches the ground and changes its direction. So basically, we see that at the beginning, the ball never touches zero. The fact is that we are missing this event because it happens between two steps. We can also see that as we have a step of 0.1 second, the time required for the velocity to change from a negative value when it is descending to a positive value when it is bouncing is not zero. It's not even close to zero. It's 0.1 second is the step size. We have seen a possible solution: decrease the step size. What happens? Okay, it solves the problem. We can catch the event of touching the floor. But we have seen also that this comes with a price. We are increasing the time for the required to run the co-simulation. But with the feature from FMI 3.0, the early return when an event is detected, in our case, the event is the change of the direction of the ball, we can basically trigger one more step when the event happens, and so we get the good behavior, the expected behavior, in which the ball hits the ground and changes its direction, and we can catch it, so we can force our co-simulation to stop at that time when the ball hits the floor, do some changes, and then move on. So the result is that we catch with the two-step function the event in which, at least the first one, in which the ball touches the ground, and so we can see that the speed is immediately changed from a negative value to positive value. And then we go on with another step and then another step, and the same happens, of course, every time the ball hits the ground. So this is even more precise than the reduction of the step size, because even with 0.001, we could have lost a fraction of time in which the ball actually bounces. With this method, we precisely catch the event of the ball hitting the ground without compromising on the step size. Here, the step size of this co-simulation is still 0.1. Okay.
How does it understand that, for instance, if from time step 5 to time step 6, it sees a change in the direction of the motion? How does it understand that? How much should it reduce the time step or go back and resolve the solution to see that exact moment that the event happens?
It has, so the FMU has some APIs to notify the event to the master algorithm. The master algorithm performs an early stopping, so stops the execution of the FMU at that time and applies the same for all the other FMUs. It is not the case in our system because in our case we have only one FMU. But if you have more FMUs, the FMI 3.0 allows the master to actually trigger the step precisely, finish the step precisely when the first FMU detects an event. So the scenario is one of the FMUs involved in the step detects the event, notifies the master, and the master notifies to all the other FMUs the specific time of ending.
So, but this might mean that for the other FMUs, you might have to revoke certain time steps. So, but here this is called early return. So you trigger a do step over a larger time, then the FMU tells, oh, something has happened in between. I don't want to make the whole time step. I return early, and then the master can react to that.
So if we have used no events in our modeling, then it's not going to detect that, or no, it's not related to that. That's other criteria.
It's the
In our Modelica, for instance, we are exporting FMU from Modelica. If we use no events in our modeling, is it going to detect or no?
You shouldn't have to worry. If you don't have these discrete events, then you shouldn't have to worry.
So it's the FMU, is the model of the FMU that somehow should raise the event. It's something that the developer of the model encodes in the model, not automatically done by the FMUs.
So if we have an if expression in our model,
For example, yes.
Yeah, that's an event. But if for the sake of, I don't know, improving the speed of simulation, we decide to remove no events, I mean, it's not a correct use case for no events.
But here you have to see whether you want to expose this event more or less to the co-simulation level. Let's say if you have some event in between your model and you have lots of damping and whatever until this signal gets to the interface, then you don't have to expose this event to the outside. Here it's more really, this is a very rough change of the model that you change go to the opposite velocity or so. So this is something, if you have such thing in co-simulation, then it is a good idea to hit exactly this point. And this is more about if you really need to cover the events, then this event mode or early return is important. In other cases, you can have events in classical co-simulation. It just doesn't matter because it's far away from the interfaces.
Can I add something for you? If you could scroll with no events, notice that the model in the previous one. So notice that the model is still detecting an event. The FMU internally is detecting an event and reacting at the right time. But the importer only sees the before and after the all colliding.
Yeah. So the most
This doesn't necessarily speed it up much because you're still doing the event detection, which is doing this.
this is what we see as an outsider. So what the other FMUs see internally, the FMU performs the right behavior of the ball. So the ball hits the ground and then bounces. It's the ground and bounces and bounces and bounces. So it doesn't perform. It performs the correct behavior. What we see outside is this behavior, and this is it's correct, but we are missing something. We're missing something. Yes.
On the system side, is there another factor that is affecting the accuracy of the time? In this case, for example, we don't detect the X moment because of this side. Is there another factor that is affecting this behavior?
Well, of course, we assume that the models are written correctly, of course. So if there is an error in the model, then the error, of course, is the standard cannot detect error within the model. And apart from that,
yeah, you have the detection, the event detection itself, which has errors, because you only find out the ball across the floor after you actually cross the floor. And internally, the model kind of goes back and tries to find some exact mold, but it's numerical accuracy. Yeah, and of course, the internal model solver is making mistakes as well. Usually, this solver, I think, is decoupled from the communication step size of the do step, but in many FMUs, the two are the same. So actually, then you really directly cause more error by just wanting to block less.
For example, if the internal solver of the FMU has the same step at 0.1, also the internal solver can miss the event, of course.
Please recommend the solvers are different that they work at the same.
Usually, the internal solver should run with a lower step size to be more accurate. Of course, this has an impact on the performance. The lower the execution, the higher the execution time. But you don't have to force the same set size on one side and on the other. Of course, you cannot have a bigger step size inside the model than the outside step size. Okay, any more questions? Okay, so just one note, for the first part on the IntoCTS application, you will find slides. I haven't followed the slides, and you will find slides with the same images of the operations that are done on the IntoCTS application. Am I on schedule?
Okay. Then we, yes. We come to the last part where I want to give some outlook on FMI3 because it gets more and more important. So I will just in short notebooks, also using this FMPy, will show some demos and also give some other demos on slide. So we already saw this overview, what is new in FMI3. And I will now more deeply go into each of these topics. So, okay, this should be FMI. So in FMI2, we have more abstract types. So for example, the data types. For example, you have a real number, but you don't say, is it a real 32 or a real 64-bit? And then in principle, you can even change header files and change this, but this was not really good. And here in FMI3, we have really concrete types, so you can much more fine granularly define the data types. Also, for example, for the integer variables, you can define if it's an int 16 or whatever. So for these applications with virtual ECUs, for example, this is important. So if you look in the model description file, so in FMI2, you will see just real as a variable. And here in FMI3, it would be like float 64. So this is really much more fine granularly defined. And also a new data type was introduced, that is binary data. And you can define a MIME type, and then you can pass more or less everything over such a connection. So even during the prototyping of FMI3, we had here an example from ADL very fast video stream over this connection, and then it was passed to some face recognition algorithm. And you can also do this with FMI. And let's say you can use this MIME type mechanism to tell what is contained in this binary data, and then totally new applications come into play. As already mentioned, we have this array variables now in FMI3, which for large data and matrices and arrays gets much more efficient, because in FMI2 there was only a naming convention for arrays. So you still can write, let's say, matrix A with a bracket in the index, but under the hood, every index variable had its own scalar variable. So if you set a matrix, so we can also show this in one of these little demos. Okay, now I will not bring it up differently. So just a second, I will change here presentation. Everything is very slow currently, sorry. Okay, so I will show it in Colab, and there this works better in Chrome. So I have opened this previously. The links are shared. So for example, for these array variables, we have now this this FMPy that we also saw previously. We have it running in Colab, and this here does just the installation of this FMPy, and I clone then this repository, and then we will see what is shown here, that let's say with FMI2 means, as I mentioned, for example, for such a matrix, you have really these are all are different scalar variables for each index, and with FMI3, and also let's say from the setting, you have to really set for each variable. You just have to set it separately. And now with FMI3, it's just one call where you can set a whole matrix with one set and get call. This is much more efficient. Okay, the bouncing ball example was already shown. So we'll go over this. Another thing is here comes an example for the intermediate variable access. So the big bullets are the communication point in a co-simulation FMU. And you can imagine here that internally the FMU calculates the smaller time step. And previously in FMI2, there is no way you can get this information out, even for displaying. What we see here would not be possible. So, for example, your tool would typically display this with a linear interpolation. But here for display, even more important for advanced co-simulation algorithms, it's good to have information also during this due step, and you can exchange this. And there are certain co-simulation algorithms that can make use of this for interpolation, extrapolation, whatever stabilization. So advanced co-simulation can make of the use of this intermediate variable access. And also this would be available in such a notebook. Okay. So we can look at this intermediate update. So also, okay, here, okay, there's something got wrong with this installation. So I will not show this, but more or less in this, you would see that we can, here in the visualization, we could see these intermediate variables. A more advanced example for the clocks, for the discrete behavior. So this is something that Claudio created. I will not go here into details, but this is there's also a paper published on this, which is, I think, also referenced here or can be found when you Google. And there you have, or perhaps Claudio, do you want to explain it on your own, what can be seen in this example? Yeah, okay.
Because from the back
yeah, thank you.
So the goal of this example is to kind of give you an introduction to the synchronous clocks, how they're used when connecting multiple FMUs together. We created a dummy system of a controller in the plant, the typical control loop, and then we have a supervisor that changes the parameter in the controller occasionally, just to really demonstrate the use of clocks. The controller has a time-based clock, so these time-triggered clocks are activated. The controller tells the importer, I have a preference to be executed 50 milliseconds, every 50 milliseconds, but the importer decides exactly when, numerically, when it runs. Right, so it will be approximately every 50 milliseconds. That's why it's representing the picture here. And why is this nice? Because if you connect multiple FMUs that all need to run synchronized, they can all express their preferences, but then the importer can actually see, okay, these are actually synchronized because they want to run both every 50 milliseconds, whereas these others are running twice as fast as the first ones. So this kind of comparison between execution rates of different FMUs is something you can easily do now with clocks, whereas before it was really hard because you had to compare readings, floats, and establish that they are some frequency, and that's like, right? That's a problem synchronous clocks are solving. And then we have the event-based clocks, which there the FMU is really the master of time. So you have an output clock here in the supervisor, and it's really the supervisor who says, now this clock ticks, right? And in here, when the clock ticks of the supervisor, then we are activating the clock, so the importer's responsibility to activate the clock on the controller, and then exchange the data. So these are clock variables, which means they are only queried and set when the corresponding clock is active. So the data is only exchanged when the event happens. Yeah, and then, yeah, so you have a dummy simulation here where you can see the controller is executing periodically setting an output on the plant, just driving the plant upwards, and then occasionally the supervisor, actually I think when the plant exceeds 3, the supervisor changes the direction of the staircase on the controller, and then the controller does this. So you get this kind of dummy.
So I think to go into the details, this would be a tutorial on its own, but to give you the idea, and I would later also bring an example where this really goes into real life now, and also more and more tools support these clocks, including MATLAB Simulink, for example, the time-based clocks. And I will show applications from automotive where really the clocks get very important now. And this is really, for discrete behavior, we have made a very big step forward and brings new applications. So the terminals, here's an example from AMOSIM. It's a tool from Siemens. And here they have their native models, and they are typically similar to Modelica, that you connect components with a single line, and under the hood, different signals go in both directions. And here is an FMU, this thing here. And now with the terminals, you can also do the same. So under the hood, there's still causal signals. The terminals are just a grouping of different scalar or array signals, but still they have a causality with the direction. So if you would look here under the hood, you still see signals going in both directions, but you can group them on the graphical level to a single line via these terminals. There is also a progress in optimization. So even in FMI2, you can get, as an optional capability of the FMU, you can get directional derivatives, which can be used for sensitivity analysis, optimization, and such things. And in FMI3, we have now also the adjoint derivatives, which also are beneficial in certain kinds of optimization and parameter estimation. So for example, currently in parallel, there is a tutorial from the Casadi developers, and they heavily work on FMI support there and make use of these new features. And I mentioned these layered standards. So the FMI standard, even though that it has about 100 pages, if you print it out, it's still quite compact. And more use cases come in. So one alternative would be to blow up the standard and have it 500 pages or whatever. And perhaps those of you who know the O2SAR standard that has several thousand pages and no one can read this. So here the idea is to have extensions possible in a separated way. And this is the concept of layered standard, that the core standard already provides extension mechanisms that you can use for certain domains. So perhaps if you are not into automotive network communication, you don't want to have in the core standard something about the CAN bus or whatever, but in a layered standard, we define how to use the FMI3 means and describe, for example, such network communication. And here, from the FMI project, we have already released 2 layered standards. One is for XCP support. That's an automotive calibration protocol. And now a very big one, this is for the network communication, where you can, let's say, model network communication with certain bus protocols with the means of FMI3. And I also have a separate slide on this. And more is coming. So we have in work a layered standard for structuring of data. First use case is here. We have now the array variables, and you can combine multiple arrays to describe, for example, a multi-dimensional map or curve. And so this gives more semantic meaning to existing array variables inside the FMU. And another thing is here, this LSREF. This will be a standard to include, so it contains 2 parts. One is to include certain reference data and let's say smoke tests into the FMU. For example, input and output reference results that you can use for the FMU. And the second part is additional files like parameter files. So we heard in the SSP standard, one part of it is defining parameter sets. And for example, you can use these XML files that you already use in the SSP standard. You could just pack it in a defined location inside the FMU and then provide variable parameter sets for your FMU. Regarding this layered standard for network communication, as mentioned, it uses the FMI3 means and more or less all of this. So let's say anyway for virtual ECUs, you use all this fine granular data types, you use the binary variables where you can, for example, a complete frame of the CAN bus you can expose as a binary variable. We have the clocks to describe certain, let's say, calculation grids, the terminals to group lots of signals. There are 2 abstraction layers. One is the high cut, which is more abstract and more or less exposes individual signals. And the other is the low cut, where you have more the complete frames, for example, for such a CAN message. And if you're more interested in this, there's tomorrow a talk in the session for layered standards, where we will explain this in more detail. I mentioned this LSTruct, so this is currently almost ready. So there's an alpha release out, and I think we will finish it this autumn and release this LSTruct layered standard. And there is a lot of other resources. So there's the FMI webpage, here this tool list, the validation tools, a list of publications also from previous conferences. We have a set of reference FMUs, which is a good starting point to understand the, let's say, basic concepts, which you can also use if you implement the FMI standard in an importing tool. You should always try it out with the reference FMUs. If you have technical questions, there you can tag questions on Stack Overflow, and normally the community answers there. There is a LinkedIn group that is here marked as unofficial, but it's I think mainly I maintain it, so I will also reply there. And but everyone is welcome also to post there. And also, I think you now know me, so either you can contact me via email. I think that the email addresses were on the slides. Otherwise, just ask me or contact me on LinkedIn. So if you also in the future have any questions, just contact me or the community. Are there, okay, here are our email addresses, yeah. Are there further questions or comments?
I'll also say that if you have any feedback on the tutorial, just tell us quietly without hurting your feelings. Then we'll try and improve this.
Yeah.
I have some questions. At some point, you displayed a slide talking about intermediate value. I didn't quite get the message of the slide.
Yeah, it's just what wants to tell in FMI3 there is the optional capability to get in and out information between the communication points. So we heard in FMI2, you set a value, then for a co-simulation FMU, then you make the do step. In between, there can be many time steps, but you have no chance to interact with the outside world during this time of the between the communication points. And now with FMI3, there is a means, even though let's say you trigger a FMI do step, which let's say advances the simulation time over a defined period of time. For continuous changes, you can still exchange information with the outside world and advance the co-simulation algorithms by that.
So it's the FMU that decides to exchange those information, and it's the master that is requesting.
So the FMU must have this capability. So there's a capability flag inside the model description XML that it can provide intermediate values. And then I think it goes in both directions. You can
just want to clarify. I think your question is who initiates this
interaction?
Yes,
it's a callback.
Yeah.
Yeah. So you know how Rumschutter evaluates nearly 4 or 5 times. The idea is that you can change the numerical solver so that in those evaluations, the numerical solver can call this callback to get intermediate values of the inputs most accurate time.
Let's say you have 2 or more FMUs communicating with each other, and the first and one FMU decides like he detected an event or something, and he wants to report the value. So he sends this value to the master, and how does the master communicate back this information to the people?
That's tricky because, as I understand, this is more like the master can provide an interpolating function.
Yeah, exactly.
So if one FMU can provide an interpolating function to the master, then the master can put this interpolating function behind a callback that then the other FMU uses. Then you're good. But if you're trying to make FMUs communicate with each other during those events, might as well use a small step.
Yeah. So this is really done by the master. It's exactly meant for such things like interpolation. So, for example, if the master gets, so even if you simulate different FMUs, you wouldn't even have to do it at the same communication step size, but the master can do some magic and then interpolate, for example, the outputs of one FMU and pass the interpolated values to another FMU. And such things can be done with this intermediate variable.
And so the other FMU will not be disturbed because it is a FMU B who is receiving this interpolated input. He is already doing 2 steps, so it's going to interrupt these 2 steps.
Yeah, inside it, so it can communicate via this callback.
If you have events, you probably don't want to use this mechanism.
Yes.
Very, very modern.
Now,
Same I see it.
this is only meant for continuous changes. So for events, there is the event mechanism. Yeah.
I would like to add something. So in the previous part, we have created connections between the output of one FMU to the input of the other FMU. But the exchange of data is actually performed by the master admin. There's no connection, direct connection, FMU to FMU. We are creating the link between the variables, but actually it is the manager that collects the output and forwards it to the input of the other FMU. So there is no direct connection between FMUs. Everything happens through the map.
Yeah, okay. Yeah,
And
I get that, but I was wondering, like, how does one output from the FMU has been disturb the process of another FMU doing these two steps?
Yeah.
More on this side.
So perhaps we can discuss it also in more detail. Perhaps you can also look at the specification. There is also explained with some visualization. And perhaps one must say one has different use cases. So in the numerical simulation with differential equations, also in co-simulation, one does such things, such like the master algorithm does interpolations. In the discrete world, like for example, when connecting virtual electronic control units, it's more a discrete thing. There you shouldn't do such interpolations. And there we talk also about such things like direct connections and optimizations for that. So for example, one idea for FMI 3.1 is to enable more efficient ways of passing information of FMU, even with such things like a shared memory or such things. And there you would avoid lots of gets and set calls where you copy values around and so on. This would be optimizations for certain more discrete use cases. In the co-simulation world, more the numerical thing, co-simulation, there you do more, you can have advanced master algorithms that make use of such interpolations and extrapolations, for example. Perhaps it would be nice to get some feedback. Is there suggestions also of what you would like to improve? Did you like it, or other comments?
Thank you very much. I hope not helpful, but yeah, the FMI3 stuff is very interesting to me. I'm working with that and doing my PhD in a related thing. So it was nice to hear that the experts talk about clocks and early return and all of that. My co-simulation algorithm. Yes, no, generally for handling events and predicting events. Also,
Good one that has the most.
Further comments?
It was good. It was a great overview. There's no way I'd be able to keep up with practically following along.
Yeah.
But all your materials available.
They're available, yeah. So take your time and go through it, and also later you can come back to us if you have questions, yeah. So I messed up with part of the recording. I will try to fix this, but at least the interactive part was recorded. You can get through this, and we will record again the first part, which was more a presentation. So we will provide with some time delay. We will provide it recorded. There is the recording from the Modelica Conference 2023 available on YouTube. So it's very similar, a little bit fewer talking about FMI3 because that was very new at that time, and now it's more established. But let's say the basic parts you can also already see on YouTube. Yeah. Okay, then thank you very much for your attention. Then we finish in time, yeah, and we have lots of time during the conference, so please come back to us, talk with us if you have any questions, yeah.